Let's give a warm welcome, as we invite on stage my friend, Marc Hamilton, Vice President of Solutions Architecture and Engineering at NVIDIA. Marc, over to you.
Well, you can tell that was an avatar because in staff meetings, Jensen never says, "Over to you, Marc." It maybe isn't too long before I can attend more SC meetings by using an avatar, but I think I'll keep coming to the DDN one in person. It really is a unique partnership because, of course, not only does DDN help us sell a tremendous number of DGX systems, but of course DDN is used in so many HPC centers and so many AI centers that are powered by NVIDIA GPUs and all of our other OEM partners' products. But also, as Jensen said, we do use DDN throughout our own complex of GPUs, which includes not only Selene, it includes a new system, EOS, which I'll talk about, and it includes includes tens of thousands of GPUs. That's our last number. Let's see, we don't have a timer going here, and so we're good. Okay, well, just kick me off stage whenever ready to go. I was at the Dell user group before this, and I spoke right after the Intel marketing speaker, and he gave a funny look when I put up this slide. He said, "Moore's law isn't dead," and of course to KLA. I don't know where the speaker went, but I think in that supercomputer with the blower on the top, I'm not sure about that model, but I think they have quite a few GPUs in the back that keep Moore's law going. But of course, Moore's law, as far as how many transistors we get in those fabs that of course are filled with KLA equipment, we still continue to get more transistors. But Moore's law has meant sort of two things over the last 50 years. It's meant one is, of course, it's meant performance has doubled every 2 years or so. And that means that over 5 years, performance would grow roughly 10x. The other thing, of course, the Moore's law is an observation of the demand curve, right? Intel and AMD wouldn't keep on demanding that all the fabs, and the KLA supports that many more transistors, smaller and smaller transistors, if the demand wasn't growing at 10x every 5 years. At the Dell user group, again, I should have copied some of the slides. The U.S. Department of Energy presented on their CTS, or cluster computing procurement project, and they claimed over the last 5 years they've gone from 4 to 5x performance improvement. So even according to their very sort of best minds in the world, only getting, and this was on CPU systems, 5x. But if you go just over the last couple of years, really, we're growing at a rate on CPUs of 2x every 5 years. And so that means if your demand curve grows at 10x every 5 years, but your CPU only compute grows at 2x every 5 years, you need 5 times as many CPUs, 5 times the power. Now, 2 years ago, well, we didn't have SC 2 years ago, but if we had, right, the world's data center usage was 0% of power. Clearly wasn't zero power, but it rounded to 0%. This year, for the first time, depending on what analysts you believe, 1 to 2% of the world's power is used by data centers. And if you look out 5 years, no one is going to want to spend 5 to 10% of the world's energy on data centers. In Germany, where they're shutting down large manufacturing plants for the winter, nowhere in the world can they afford to do that. In fact, we're working with a large European customer working on a new procurement for an exascale system, and they're looking right now at their power budget and saying, look, we think even with GPUs, we think we're going to have to shut down the system 30% of the year in order to meet our power budget. We're actually working with them so that they don't have to turn off their system 30% of the year by really looking at power efficiency. We got a funny pop-up here on my screen, but let me see if we can advance it there. There we go. So in NVIDIA, when we talk about NVIDIA as a company, of course, we do a lot more than just chips today. We do 3 chips that are on the bottom. Of course, the GPU, our new Grace ARM-based CPU, and our DPU, the evolution of the NIC, or data processing unit. And in fact, DDN, we're working with DDN on designs that include all 3 of these products, not just the NIC. So a lot of exciting things. But above that, of course, is all of our different server packages, including the DGX. Most of those servers are all our names for the different OEM servers. And then above that, all of our software. Many of you know CUDA, but today we have over 350 libraries or software development kits based on CUDA. So we listed just a few of them there. We have so many SDKs, we now simplify it into 3 different platforms. Our NVIDIA HPC platform, all of the SDKs used for traditional scientific computing, our AI platform, and then the NVIDIA Omniverse platform for building digital twins, like in avatars, like the one that you just saw. Above that, we have a series of different AI frameworks addressing different common AI problems. And many of them, again, are in use by customers around the world. Just to name one, NVIDIA Metropolis is our AI framework for intelligent video analytics. And going back to the CDAC presentation, again, another DGX and DDN user, you saw many different sort of smart city applications that needed intelligent video analytics. And NVIDIA, of course, doesn't provide the end user solutions, but again, it's a platform for developing intelligent video analytics. It's things like sample AI models, sample training scripts. And if you think about it, the AI revolution has really changed the way that you write software. If you go back before about 2012, so go back 10 years and earlier, scientific computing software and all software is written by an engineer typing at a computer. And you really didn't need a lot of DDN, Lustre storage to type the software that was being written. But of course, what you use that high-performance storage for was either to record observations from instruments, be it a space telescope or a KLA inspection machine, and of course to record data from simulations that were simulating scientific things you were not able to observe at that time. And that's where all the data storage was. Now, starting in about 2012, the big bang of modern AI, data became the source code, right? And so again, in CDAC, their data for going through and building smart camera applications, intelligent video analytics applications, is not an engineer typing at a terminal, but an engineer bringing in petabytes, terabytes of data, feeding that into an AI model, maybe from Metropolis, maybe somewhere else, and then developing then a deep neural network. And that process needs to repeat over and over again with that data scientist picking out different types, different subsets of images. A typical imaging application today will use about a half million images, typically at 2 megapixels or greater, and train on a single DGX system for 8 to 10 hours. That's just to train one network one time. If you think about a self-driving car, a fully complete autonomous vehicle will probably have about 100 different AI networks operating inside it. So again, just petabytes and petabytes of data that needed to be stored. The largest sort of new type of AI model is these so-called large language models. Again, to give you an idea in the speed of innovation in the AI space, large language models were made possible by a specific type of deep neural network introduced by Google in late 2018 called the transformer. In fact, if you plot all of the AI models, all of the AI deep neural networks that have been developed since 2012 to today, you see that they're growing at about 10x Moore's law. So performance, instead of doubling 10x every 5 years for the last 10 years, has grown 100x every 5 years. On the other hand, since 2018, the transformer models, the performance growth of transformers has grown about 1,000x, about 1,000x Moore's law in simply 5 years. That was the original Moore's law, not the current Moore's law. Now, large language models, we all are familiar with GPT-3, right? It reads in all of Wikipedia. You ask it a random question. It can answer the question, sometimes with some miscellaneous or interesting garbage, because it's, everything that went into Wikipedia or everything that I read on the internet, it takes in. To train GPT-3, takes about 5,000 GPUs running continuously for 1 week to train, just to give you an idea. And that's just training it once. And again, remember, you have to train a model 50 or 100 times. If you want to use GPT-3, they have an API for it. There's other competing systems, Hugging Face and others, that now have put up APIs, and they work great in English. If you go to China, there's similar types of models that work great in Chinese. If you want to go to like the next 40 or 50 languages in the world, including Hindi, and again, India alone has, anyone know how many languages are on India banknote? Anyone from India know even? 46 languages just on the Indian banknote. So again, that's 46 languages right there that GPT-3 doesn't work on. And again, if India wants to go through and have GPT-3-like capabilities, they need to tune them. But again, besides spoken languages, again, great ideas get copied many, many times over. We see a number of different use cases of large language models. A great and topical example is used for genomics. Right? Genomics is a language. Now, it may seem like a simple language, only 4 or 5 characters, but if you think of it, the COVID genome, right, is that entire genome is huge, the different combinations of that, and that total then genome becomes the language. A set of researchers from Argonne National Labs, from NVIDIA, and a number of other institutions around the world collaborated on building a large language model and trained it on the COVID-19 genome. They were then able, just like you can ask a question to GPT-3, they asked the model, what would future variations of the COVID spike protein be? And again, we don't know if these are successful, right? But again, time will tell. But then again, biologists looking at this, scientists looking at this said, that makes a lot of sense. Given the variations that we've seen in the spike protein and in COVID, this model predicted new variations. Why is that important? Well, if you can predict a new variation and look for it as people are being tested for COVID, you can stop much earlier outbreaks of it. So again, another area in a much more commercial application is in financial services. Financial services, think about it, all have tremendous amounts of tabular data, credit card transactions, checkings account transactions, etc. You say, well, is that a language? Well, it is representing a language, right? And so using NVIDIA Rapids, we're able to take that tabular data and input it into a large language model using NVIDIA Megatron, which is a GPT-3 type model. And we're able, and in the financial services use case, it's very interesting. People are concerned about either data privacy or going through and predicting specific types of behavior. What is the average spend going to be of someone attending SC13 and going out to dinner? Guess it depends if you're paying for it or if you're getting a partner to take you for it or what your spending account is. But anyhow, right, financial services companies want to be able to go through and generate data without having to be that is similar to all of their stored data, but isn't tied back to a specific individual for privacy reasons. And so using what we call Fin Megatron is being used by a number of financial institutions to do that. And how many more use cases are there going to be for language models? We just don't know. But these are all tremendous drivers of storage and of course, compute as well. since we had that nice little avatar at the start, I thought I would talk a little bit more about a new product called the NVIDIA Omniverse Avatar Cloud Engine. This will run as a cloud service. Of course, you can run it on your own instance of Omniverse. And what will it actually go through and include? So give you a little bit of the software stack there and showing you. And again, you see different components. The Riva speech engine, animation AI, rendering capabilities. Just like the self-driving car that has many, many different models in it, to bring you that Toy Jensen application requires a number of different AI models. And again, all operating in parallel to go through and put together that. And so here's some different examples of some advanced work in avatar design. The first one is some work out of NVIDIA research called our 3D audio to face. And when you see the results of this, you say, well, wow, that looks pretty amazing. How do you take just text and go through and animate the face, the face there? We've actually gone through and trained the deep neural network to learn the muscles of the face and how the muscles of the face move based on different words and different emotions behind those words. So let's go ahead and see if the video plays. So this is inside Omniverse Create, and you see the user here is going through and adjusting different emotions and showing how that reflects in the face in the model.
It's so dark. Where is it? I can't see it. I can't see anything. But I know it's there. Waiting.
The beige hue on the waters of the loch impressed all, including the French queen, before she heard that symphony again, just as young Arthur wanted.
Okay, I have a few jokes here. What do you call a fish without any eyes?
I know that's a bad joke, but we had in there before the waiting, and then it said something about another vendor's CPU, and marketing said, no, take that out. You can't use that. So that's only for NVIDIA internal audience. Now here's another type of ACE example, and this is just taking a 2D image of a face and animating the face based on the 2D image.
Lately, I've been thinking, I want you to be happier. I want you to be happier. When the morning comes and we see what we've become. In the cold light of day, we're a flame in the wind, not the fire that we begun. Every argument, every word we can't take back. Cause with all that has happened, I think that we both know the way that the story ends. Then only for a minute I want to change my mind, cause this just don't feel right to me. I wanna raise your spirits, I want to see you smile, but no, that means I'll have.
So we're going to stop at that. But again, why would you want to do that? Well, think about any sort of call center interaction, right? And again, in the future, of course, people are, teenagers today don't want to interact with just a voice on the phone. They'd like to go through and talk to at least a semblance of someone that looks like a person. And again, that discussion may start as a phone discussion, may transition to a video discussion with a simple chatbot that has a certain level of training, maybe trained on GPT-3, and then later on transition to a much more complicated chatbot, and then eventually to a human person if it's a problem that can't be resolved as you go. So this is NVIDIA Selene. A lot's been said about NVIDIA Selene, so I'm going to just sort of gloss over that. But again, coming up is NVIDIA EOS. NVIDIA EOS is, we didn't do a big study. We didn't do a study at all. We were, of course, we're always under time pressure to put together these systems. We had the first results from NVIDIA EOS, even though it's not complete yet, were submitted to MLPerf and published in the MLPerf results this week. And so we just went and called up our DDN account manager and said, we need some more DDN storage. And it was as simple as that. So the latest MLPerf number results were all trained on EOS on DDN storage. They appear in the experimental category only because while we've shipped the H100 through OEMs, in fact, we have an H100 system from Lenovo on the top 500 list. The DGX systems won't ship until late this year, early next year. So that's why the results are experimental, but they're up and running in EOS with Selene. By the way, that Lenovo system, it's a smaller system, but it did rank #1 on the Green 500 list. So we're very proud of that system that outperformed in performance per watt some of the other GPU systems from some of the other vendors. This is another real exciting set of tools. This is not a product, but as we build data centers, it becomes more and more complicated to build these supercomputers. We're working with one of the large cloud providers that's building out their next generation InfiniBand NDR network, and they have over 200,000 InfiniBand cables in their data centers for those systems. So what we did using Omniverse, if you think about it, everything that goes into a data center, the DDN chassis, the NVIDIA chassis, the blueprint of the data center, the CFD analysis of the racks, all of that exists in some sort of digital form. And the problem is it exists in 5 or 6 or 10 or 15 different tools. And never are they brought together into one place. So eventually when that tech goes out to build the data center and assemble everything, or after it's assembled and someone's trying to operate it, there's no traceability back. And so we said, well, why don't we use our own products and use Omniverse as a platform to build a digital twin of our data center. And so we did that. We did just that by retrofitting, going back to Cambridge 1, which we talked about at ISC, and we rebuilt Cambridge 1 as a digital twin. So here's a little video showing the state of the art.
NVIDIA Omniverse can be used to build digital twins of high-performance data centers to help optimize every step of planning, building, and operating complex supercomputing facilities. In constructing NVIDIA's latest AI supercomputer, engineering CAD datasets from tools like SketchUp, PTC Creo, and Autodesk Revit are aggregated so designers and engineers view and iterate on the full-fidelity USD-based model together. With Patch Manager connected to Omniverse, the complex topology of port-to-port connections, rack and node layout, and cabling can be integrated directly into the live model. Next, CFD engineers use Cadence 6 Sigma DCX to simulate thermal designs. Engineers can leverage AI surrogates trained with NVIDIA Modulus for real-time what-if analysis. And with NVIDIA Air, a network simulation platform connected to Omniverse, the exact network topology, including protocols, monitoring, and automation, can be simulated and pre-validated. Once construction is complete, the physical data center can be connected to the digital twin via IoT sensors, enabling real-time monitoring of operations. With the perfectly synchronized digital twin, the engineers can not only simulate common dangers, such as power peaking or cooling system failures, but also validate software and component upgrades for CI/CD before deploying to the physical data center. With digital twins and Omniverse, data center designers, builders, and operators can streamline facility design, accelerate time to build and deployment, and optimize ongoing operations and efficiency.
Now you might ask, how much storage do you need for a digital twin? We've started building out. OVX is similar to DGX, is our 8 GPU platform for building for Omniverse, for running Omniverse at scale. Unlike DGX, OVX is built by OEMs. So we have a number of different OEMs shipping OVX compliant platforms today, and we've built out our first few internal superpods based on OVX. We have about 400 servers, each with 8 A40 or L40 GPUs running our internal OVX workloads. We haven't sort of published that reference architecture yet, but when it comes to storage, anyone want to guess what storage we're using for our OVX SuperPod? It is DDN storage. And again, because that data needs to go back and forth from the design world over to the AI world for simulation and back and forth. So we're using DGX to span both of those superpods. Some of the other things that we're doing with EOS will be part of our Earth 2 system for climate forecasts, and we're working with a number of the large climate labs around the world on that. And so again, a lot of exciting things going there. I did promise to talk a little bit about MLPerf. So again, MLPerf isn't new. It's been going back for a couple of years now. And again, many different, over 50 different companies participating in that. MLPerf started as an AI-based benchmark, and it now includes a number of other use cases, including MLPerf HPC. And so again, sort of a broad set of use cases. Why that's important, and another example of where these in real life, the performance needed is actually much greater than any single MLPerf benchmark or any benchmark, is just take a very simple real-world application like a shopping example where you go through and you're going to have a very complex pipeline that you need to work through, where you need to do some automatic speech recognition, some video recognition perhaps, run it through a recommender system, and then at the end go through a text-to-speech pipeline. So again, today, these are all separate AI models. NVIDIA is one of our new software SDKs. It's sort of flashed up there, is NVIDIA UCF, Unified Cloud Services. Unified Cloud Services is a set of sort of drag and drop interfaces that let you compose different microservices of NVIDIA-based framework applications and create in GPU memory pipelines without doing any coding. And not only in GPU, but that ability to automatically scale that application across 8 GPUs with NVLink in the DGX platform, or even across RDMA networks on Ethernet or InfiniBand to span the data center or to span multiple data centers in very easily scale applications. So look more, UCF is in early access today, and look more on that in the way to build different applications. One of the press reports I read about MLPerf said it's getting pretty boring. It's more about NVIDIA competing with NVIDIA. And so the little green bar there is NVIDIA, and of course here in time to train at scale, you can build as big a system you want, and then you measure the time to train. So shorter, a smaller bar is better in this case. And in fact, some of the bars you actually even don't fit on the screen, have to be broken there to show. But again, what's really interesting is most of the applications, NVIDIA is the only person actually submitting the application, but Jensen still really likes to submit them. They're the new MLPerf HPC application, so we submitted results in those. If you look at where the new sort of exascale class of AI performance supercomputers are around the world, more and more of them today built on NVIDIA technology. And finally, one interesting thing to talk about is the emergence of really HPC at edge applications. HPC used to be all about the supercomputer inside the data center, and today more and more HPC is about managing large scientific instruments, the square kilometer array, a particle physics accelerator, an electron microscope. In these new instruments that sit at the edge, so to say, is they generate so much data that you can't bring all that data back to a supercomputer. Typically, you use some sort of FPGA to do real-time data filtering. FPGAs are good for that, but again, FPGA is very hard to program, so typically you do some basic filtering, you put it in the FPGA, you deploy that out in the instrument, and well, if that happens to filter out the data you need, it's gone forever, right? And so again, today, by putting GPUs at the edge and storage at the edge, and combining, in certain cases, bringing the compute to the storage instead of taking the storage or the data and moving it to the compute, is a new paradigm. And again, to program these applications, the unified cloud services, to let you go through and create these pipelines. In the past, had been very sort of custom FPGA programming, now able to do that in a drag and drop fashion. So that's it for today. I'm not sure if we have time for Q&A because the time schedule when I started was a little bit different than what I had. But thank you very much for inviting me, and hopefully invited back in the future.